So the input, the output, and then we have the memory, a very important part. And then later on, we actually say that the program consists of instructions as well as the data is in memory. And then we have the processor here. Okay, so I think in the past, few weeks, you all have been doing programming and using the various peripherals on the system on chip, such as UART and I2C and all that. But you may have forgotten that actually the computer system consists of all these basic parts. And then the registers is inside here, right? And they're all joined by the interconnection network. Then we talk about instructions, and one word, is 32 bits. Very useful to draw a rectangle to represent either a register or a word in memory. Then we look at a simple program, but there is this nice diagram that summarizes various things a bit later on, and I'll come to that. Also, make sure you know the important registers like program counter and instruction register and so on, and also the general purpose registers. Okay, I'll come to this more complicated big diagram that involves instruction, that involves data a little bit later. So let me just come to it. Of course, you need to understand that memory is a bunch of words that are 32 bits wide. Okay, 32 bits wide. Every single bit is just a 0 or 1, right? And we give an address to every byte. So that's therefore for the whole word, from one word to another word, the address will jump by 4, right? I suppose, in the recent weeks when you were using C programming with the CMSIS library, you were calling a lot of things by name. So you may have forgotten that actually, at the end of the day, those pointers or pointers to structures, for example, that we talked about earlier on, actually maps to physical addresses. Right? I showed you the LPC17xx.h file. And then I suppose in the past few weeks, you all have been happily calling various functions to read the light sensor or do UART and all that. But at the end of the day, you have made use of those pointers, structures, and all that. So, okay, I want to come to this diagram. Okay, you should also know about the differences between reduced instruction set computer and complex instruction set computer. For the reduced instruction set computer, the instruction is at most 32 bits or 1 word, right? I mean, in our 32-bit architecture. If you have a 64-bit architecture, of course, it may be 64 bits. But for RISC, the 1-word instructions, right? And actually, if you were to do any arithmetic operations, the operands or the values that you work with must be already in the processor. Okay. So these registers may be, it would have to be in the processor registers already before you can add them, for example. And then for complex instruction set computer, you can have an instruction like this that seems to refer to things in memory. So the programmer only writes this instruction, but actually at the end of the day, before the addition, even in complex instruction set computer, they have to copy the data values into registers before they can be added. Very important thing is the fetch and execute, right? So So this is the very important diagram. Make sure you all understand this diagram. Okay. So if you have your program in memory, right, and then this is also memory. Although I draw it separately, but actually this thing in memory, this data, this program, they're all inside this box. Right? They're all inside this box. Okay, let me use this instead of my laser pointer since it's a bit. Maybe I'll use another color. Maybe I'll use purple color. Okay, no, my red color is fine. Okay, so okay, this thing is inside main memory. This thing is inside main memory as well. When you actually execute the program, right, it has to do the instructions one by one. And the instructions, don't forget that in memory, the memory is dumb. You cannot do anything there. So there's the fetch part, okay, that essentially copies that instruction inside the instruction register. Okay, so the load R2, A comes inside here. And then after that, you have the execute part. So the number one execute is actually what you're supposed to do. You're supposed to load the value A into R2. So when you execute the first instruction, it causes this value here to be copied into here, right? So that completes one instruction, the fetch part, which is the instruction itself, and the execute part, which is the action of loading the data value from memory into R2, right? Then after that, you know, the same story goes. Your program counter is like a bookmark. It will actually, as soon as you have loaded or fetched one of the instructions, it will jump to the next address, and then it will cause this thing now to be copied here. And then you will, when you actually execute for instruction 2, it will cause this tree to come to R3. And then now, the third instruction is slightly different. You still have to fetch it, so every one of these instructions have to be fetched. So number 3 fetch comes inside here, so this instruction happily sits in the instruction register. But then when you actually execute it, this time it is just doing addition of the value in R2 and R3, and it's done by the arithmetic and logical unit, and then the answer puts here. So that's the execute part for instruction 3, right? And this one, the action is just adding. It doesn't involve anything from memory. And then finally, the 4th instruction, you also have to fetch it. And then it comes inside here, and then when you execute it, this time it is taking whatever is in R4, cross back to the memory to put it here. Okay, so the execute part for instruction 4 causes this to happen. Okay, so make sure you understand this what's happening in this slide 29. Okay. Any questions on this? Yeah. Okay. You know, then the rest is just explaining this. The last part of this lecture 2 is to do with manipulating the program counter, right? So if you change the value in program counter, it will actually cause the program to be executed in different ways. So if you don't do anything, the program counter, as we saw just now, you fetch one instruction, it will automatically +4, and then after that, the next instruction in the next word will be fetched, right? So if sequentially you don't do anything, it will be sequentially. But if you want to do a loop, very easily when you reach the end here, you replace the program counter value with the with this address, and then you will go and fetch this instruction again. And after that, you don't do anything, it will just by default go to the next one, go to the next one, and all that. And then you can repeat this many times, and that's how a loop happens. Same story goes for when you want to branch to another part of the program, or you want to do a subroutine call, and later we'll talk a little bit more about subroutines. You just need to change the address value in the program counter, and you can jump all over the place. Okay, so make sure you understand this mechanism of program execution control. It's just a matter of changing the value in the program counter, and we discussed this in tutorials as well, right? Okay. So, and then one last part is the condition code flags. Very important for helping us get conditional execution later on. Like, if x is less than y, then do this. If x is the same as y, then do that, or whatever. And later on, when we come to lecture 4, we will actually look at those conditional execution that involves the IT block and all that. But for now, it's just telling you that you have this bunch of condition codes, and later on you'll see that these are very useful, right? Okay. So I think that's all I want to say about lecture 2. I move on to lecture 3. Any questions on lecture 2?
If the sign assign, I have two complement number adding together. Will we trigger the carry as also the overflow at the same time?
If you have what? One sign or one unsigned?
Two sign number.
Two sign number.
Because just now you mark unsigned for the carrier. I was wondering if you will trigger the carry if it's sign number. Because it's taking the MSB, right?
Okay. Now, as I mentioned last time, the computer doesn't know whether a particular value in a memory location or in a register is signed or unsigned, right? You will see like 1010 something. It's up to your interpretation whether that first most significant bit, that 1 there, is negative to the power of 31, or it's actually positive to the power of 31, right? Then it's up to you to interpret it. When you actually store the value inside, did you intend it to be a negative number or not? If you intend it to be a negative number, then whatever answer you also have to check. Now, when you actually add the numbers together, and then you go and check the flags, right? If the flag is set for, that means if you actually intended it to be a negative number, you actually don't have to go and check the carry flag. The carry flag value, whether it's 0 or 1, is not of interest to you, it's not relevant. If you intended it to be a signed value, then you only need to check the V flag. And if the V flag is 1, and you actually intended those numbers to be negative as you said, then something is wrong. Then you cannot trust the answer in the destination register. Okay. But if the overflow flag is not set, then it's fine. It's a correct sign result. Yeah, that's all we need to be concerned with. Okay. But then if you actually intended the two numbers 1010 something, 1010 something to be unsigned, to be positive values, after you add it, you go and check the carry flag. If the carry flag is set, that means the result is not correct. Okay.
But the question is, will it trigger the carry flag?
It will.
Yeah, right.
It will. Because it doesn't know whether you are doing sign or unsigned. So you actually do both.
Okay.
It's just that up to you whether you, if you know that it is a signed number, then you go and check the B flag. If you know that it's an unsigned number, then you go and check the C flag. Yeah. So that one you have to do.
But for the overflow, if only happens when there are two numbers that with the same sign, right?
Same sign and the result different sign.
Result different, right?
Yeah. Yeah. Correct.
How about the branching up? If I branch twice, I BR twice, and then I BX, I return. Will we forget the initial address that the first?
Of course.
Right?
Yeah, of course. So if you, later on you come to subroutine, okay? If you have BL and then BL again, then you forget how to go back to the first place. Okay. Yeah. Okay, we'll come to that later. So now I want to move on to lecture 3 where yeah, so in lecture 3, we come back to the ARM specific case, right? Now it's important for you to, I think by now all you are quite expert in this. You have been using a lot of the peripherals in recent weeks. You've been doing a lot of GPIO, UART, I2C, and so on. But even within the Cortex-M3 part, right, within this part itself, okay, the registers are all inside the processor part of what we saw in lecture 2, right? So the important ones are down here, then you have the pin general purpose ones, right, 0 to 12. So this is a stack pointer. This one is a link register, this one is a program counter, and then the instruction register is not shown because the programmer doesn't have direct access to it, right? So like what your classmate mentioned, this link register is actually important when you have subroutines because the next line, let's say you have a certain main function. Now the main function can be a C program, can be an assembly language program. The subroutine can be a C subroutine, can be an assembly language subroutine. In fact, in assignment 1, you have a main C program, and then the assembly language function is actually like a subroutine, right? So after you call the assembly language function, at the end you will notice that in your assignment 1 there's a BXLR. So the R14 in concrete terms is just a rectangle register with values, right? And also for stack pointer, it is also storing some address inside. Link register also is storing some address inside, right? It's the address of the instruction after you do the PL. You will store it there so that you know how to return. Okay. I'll come to that later on when we talk about the stack. Okay, so all that status register, the NZ, C, and B. In lecture 2, it was a general case. In lecture 3, it is specific for the ARM case, right? Then you have your memory map, remember that all the rectangular boxes have addresses, and the addresses we don't write it inside the box, we write it outside the box. Okay, and then you will know that all the things that you were doing with GPIO has 200 something address. All the things that you were doing with some I2C, for example, is 4 something address. You don't have to memorize all this. Okay, so nobody will ask you, hey, what is the address of I2C0? Nobody will ask you such things. Hey, what's the address of UART2? You don't have to memorize all these things, obviously, right? You don't expect you to know. Okay, so stacks and subroutines are very important, right? So make sure you understand why you have stacks, how stacks are implemented and why it is useful. Okay, it is useful as a temporary storage place. And the stack is actually in main memory. Okay, it's not part of the processor. So I always write down processor here. This is a register. Okay, so this is not part of the stack. This is a register in processor. This stack itself is just some memory locations that you reserve to be a stack. And then we say that, oh, SP points to the first word here. When we say SP points there, essentially what it means is in the SP box, let's say this word's address is 1000800, then basically that value is sitting inside here. Okay, that value is sitting inside here. So that's why we say, oh, SP is pointing there, just to for ease of explanation, right? So actually, the push operation will cause this value to be pushed to the stack, right? But you can see that actually, when you push R0, you don't actually have to say, oh, push it to 1000800. It knows that you want to push it to the stack, and then the stack pointer is automatically keeping track of where is the topmost item, and then it will decrement it before it saves it in the next slot, right? But then you can see that anything that is causing a value to be copied from register to memory is like a store, right? So push is actually like a store, okay? And then here, you may be doing some other things. It could be, you see your C program, take the case of assignment 1, your C program is actually using the registers R0, R1, R2 until R12. You don't know, it's using some of them, right? Then you call your assembly language function that you wrote in assignment 1. The whole computer system only has those 13 registers. So you also happily go and use R0, R1 and other. Of course, those R0 to R3 values that you use to transfer parameter values or argument values between your C program and your assembly language program, those are sort of not likely to conflict because the C program knows that they're using those registers to pass argument values to assembly language. In assembly language, you know that you will find those at most 4 arguments in R0, R1, R2, R3. But R4 to R12, the C program may be using it for something, the assembly language may be using it for something, and if you go back to the C program after modifying the R4 to R12, the C program will become very confused. And then you get a hard fork error. I think quite a lot of you would have encountered hard fork error before when you didn't do push and pop. The reason why push and pop can solve or avoid that problem is because before your assembly language program go and modify the R4 to R12 values, you actually save it to memory first. Like this, you actually save all of them. Then after that, you go and destroy R4 to R12, do your own thing. And then at the end of your assembly language program, you have one example down here. You actually do a pop. You do a push at the beginning to save it onto the stack. Then you do whatever you want. And after that, at the end of the day, you pop it back. And pop it back is actually just restoring it from memory back to the processor registers. And then when you go back to the C program, right, just like this picture is showing you, this main part here may be a C program or maybe an assembly language program. Then you get back the original values and then you don't get confused. And then when you don't get confused, you don't have the hard fork error. Okay, so that is why the push and pop can avoid the hard fork error. And at the end of it, you have this VXLR. Okay. The thing is, when you do a BL or you call another subroutine, you see in this case, actually in your program there isn't this space. This line is the next thing. So this line has the address ABBR2.
when you call the VL, branch with link actually copies the current ADD, because the ADDR, when you run this, is already ADDR2 inside the PC. It saves it inside the LR, the link register, the R14. And then here, this first instruction here has the address ADDR1. It will replace the ADDR2 with ADDR1 so that after this line, it will come to this line rather than after this line come to this line, right? And then after that, happily, it will run sequentially inside your subroutine or your assembly language function or whatever, till it hits the VXLR, which actually the name tells you what it's doing. It's branch with exchange. So now it's going to swap back. It was maybe you wanted to go and do the next line here, and that next line is maybe ADDR something else. But then now it will say, oh, okay, I copied back this value inside PC, so ADDR2. And as we talked about just now, the instruction that actually gets executed depends on what is the address in the program counter. So if you swap it back, then you say, oh, next instruction is ADDR2, then it will go and happily run this one. Okay. So that's how the execution went from here to here, then back to here in the main program. Right? So we actually need you to understand this mechanism and how the role of R14 into here. Now, of course, the more complicated case is over here. You go and do another BL, right? Yeah, nested subroutine. You go and do another BL. If you do another BL, then one of those addresses will overwrite this value in LR, right? And then after that, you lose this thing when you do the, of course, when you immediately, let's say, come inside this second subroutine, here also has a VXLR, then you will come back to the first subroutine, right? Because here you would have saved that return address here. But after that, when you do VXLR, instead of going all the way back to the main program, you will actually go and get stuck inside the first subroutine, right? So how would you avoid that?
In the subroutine, check the
original. Actually, in the next subroutine, you actually make sure you push R14 as well. Okay. Or rather, you actually should push R14 even here, because if you do it in that next one, it's too late already. Because the R14 would have been overwritten before you got into the second subroutine. So here, once you come inside here, you include the R14 inside the include the R14 register on the link register among those that need to be saved. So you push that one as well. And after that, here you can go and modify R14 as well, because just like you can modify other registers and restore the other register values, you can do the same thing. So when you pop, you include R14, and then you will ensure that the R14 value that is saved in the stack will be restored, and then you can come back to this place safely. Okay. If you didn't include the R14 here, if you were to do another BL here, you cannot go back already. Every time you VXLR, it will come back to that. You will actually loop round and round inside this first subroutine, right? It's like if you have watched the movie Inception, you can dream, and then the dream is you dream again, so then you go somewhere else. Then after that, if you get stuck in the dream, you come back to real life, then that's horrible, right? So you want to make sure you save the return path to come back to real life.
As long as I push
R14.
I can have infinite.
Yeah, you can keep on nesting. So you basically have to be careful, because once you do assembly language, you are in full control. You are treated as adult. Nobody sort of prevents you from doing things. You have full control. And then you have to know what you're doing in a sense. Right? Okay. So how the stack works, I will leave you to read it yourself, but I just sort of mention a few things, right? Okay, we move on to
Do I have to concern myself with whether I'll run out of stack memory?
You should be aware that, there's limited amount of stack, there's an initial stack pointer value. Normally we take it to be 10008000, but it can be set to any other value in the configuration file. So that concept, I mean, sometimes we may test your understanding, see whether you are aware that there's limited stack space. Yeah. So you have to be aware that there's limited stack space. Yeah. Okay.
So,
Yeah.
can we push before we pop? Can we like push and we push again? Or will we pop before we push?
Sure, you can keep on, especially in the nested subroutine case.
Okay.
You'll be pushing and pushing and pushing. But remember the most important underlying principle of the stack is last in, first out. Okay, so don't forget that. When you do, let's say 3 or 4 pushes, right, and then you do a pop, the first thing that come out is the last push, not the first push. Yeah, you must, and then usually you don't have to. It will make sense for you to pop as you go backwards. You don't have to like deliberately, so troublesome, must manually pop a few times. It won't. It's very natural for you to pop as you go back to the previous level and pop again and pop again. Right? But then your last level don't sabo the previous level and go and do extra pops. Then after that you cannot go back already. Okay, then we come to the assembly language thing. Of course, I'm not going to revise everything now. So one of the most important things for all of you to make sure you understand is the load and store, right? There are 3 sort of ways of doing load and store that we considered, and you have to know how to use each one of the 3 ways, right? So the first one, and I also put the number 1 here last time, is load and store with immediate offset, which actually has the format with the square bracket, right? And within the square bracket, you see a register. That register is called the base register. And that base register will contain an address, okay? And normally, we can add the optional offset to the value in the base register to get our effective address. Right? And then the basic one is that the value in Rn is not changed, it's unaltered, remain the same. Okay? So, like this example, or maybe I jump straight to this case. Okay? So this case, the R2 is the base register. Okay, we'll see this base register again and again. Later on, I'm going to show you some past exam question that requires the use of load with immediate offset. Also, it's useful to think of certain registers within the square bracket as the base register. Right? It is the base register. Then, in order to load the value into R3, you of course need to know which value in memory to load from. And one other important thing is load always involves a transfer between memory and processor register. Right? You are crossing the river between memory and processor, and then store is the opposite, going from the processor register back to memory. So in this case, load, I have to, since there are so many words in memory, you have to know the address. Quite obvious, right? And how do I get the effective address? I will add the value in the base register to the offset. And then this value, okay, then I actually load this one. So remember that, and then note that this is unchanged. Later on, we'll look at the pre-index and the post-index case where this one becomes changed. Okay, so later on we'll talk about that. Then the second way of doing load is actually using this program counter relative addressing. But if you look at the format, it's very, very simple. It's just load to the value to the destination register that you want to put the value in, and then it's a label, right? And this label you could have defined using dot word, for example, because at the beginning of this lecture we talked about how to reserve memory and all that using dot word, right? So when you actually reserve memory and initialize it with certain values, that reserve memory holding the data value is actually placed next to your instructions in the program. So the distance between the instructions and the data is actually very close. This program counter relative addressing has a limit in terms of how big that offset can be. I think it's 4096 if I'm not mistaken. You don't really need to know this, but I'm just mentioning that there's a limit. So that's why when we actually want to load from hardware, just now in the memory map, we know that GPIO is 200 something. I2C registers, is 400 something. So if you take 400 something or 20 something minus your program code, which is actually in the low ranges 00 something, is definitely more than 4096. It's actually millions of words away. And therefore, you cannot use program counter relative addressing for hardware registers. And that's why for hardware registers in the Blinky program, you will notice that you always use the first type of load. The first type of load always works one, because that one is the basic. The one with the base register, the one with the square bracket, that one always works. Okay, so although program counter relative addressing is the most convenient, and if you find that you are loading a constant value, you will try to use this, okay, because it is so simple to use. But then, of course, what is really going on is that you have reserved memory, you have given this place a label, and then the thing that people always get confused is with equal sign, without equal sign. So the equal sign one is the third kind of load that I'll come to in a moment. But in this case, this one no equal sign. It is actually saying, hey, this is a label. Go to the place where the label refers to, which is this place. You are not going to load 1060 into R1. You're going to load 123 into R1. Okay, you're going to load this value that's sitting there. And actually, effectively, if you translate it back to the first kind of load, it is actually doing program counter, comma, offset 56, for example, in this case. And so, actually the base register can be any register. It can be the program counter itself, it can be any register. And then this will help you get the effective address, and then from the effective address, you can actually load that value into the destination register, right? Okay, so later we'll see some examples where we use three kinds of loads, right? And then the third kind is the load using pseudo instruction. Pseudo instruction just means that I'm using a few instructions to do something. And in this case, since this whole thing is supposed to be 32 bits, because we mentioned that RISC architecture, the whole instruction is 32 bits wide, then how come the value is also 32 bits? So it cannot be that this thing is fitting in 32 bits. So actually the assembler has helped you by reserving memory and sticking this value inside and then putting a label to that reserved thing and then calling program counter relative load. So it's actually doing this for you. You write like that, but actually what happens is this. And of course this will have the effect of this value going inside. And then when you actually have the equal sign, the same thing, this num1 may actually refer to this thing. Of course, the num1 is a label value that is referring to the address. When you do equal num1, the same thing happens. The num1 value, okay, is actually put inside a word. It's given at some address and it creates a label to that, let's say pointer, and then after that it also does a program counter relative with the pointer there. That's how this value here goes inside R2. And that is how you actually load the base register, because this base register is actually an address. And how did the address go in? You would normally equal a label, and then this address actually found its way inside the base register through this mechanism, right? Okay, so three kinds of load. Later we will look at some examples of this, but let me just move on a little bit so that I don't jump back and forth. Branch, easy, you can read yourself. Immediate operands, sort of operands that you can hard code as part of the instruction. Later you can add this 300 directly, but know that you cannot have super big values because it is part of the 32 bits and there's a limited number of bits. And then the instruction manual will tell you how many bits and what's the biggest value that you can have. Operand 2, just recognize the format. It can be one of three things: the 8-bit value, a register, or register with shift. Difference between move and load. Move would be, something that is transferring from one part of the processor to registers to another register. So it's solely within the processor, Whereas the load and store always crosses the bridge between memory and processor registers, right? Okay, add and subtract all this very easy. I'll leave you to read it yourself. Multiply, very easy. And then we look at all those examples. Now, you can also notice that in this case, we had the dot word, so they are very near. So I can actually use the simple one. Unfortunately, it's only available for load. For store, even though it's still quite near. For example, for the variables, we have to reserve it by .lcom, but we use the store with offset addressing in the case of, because there's no program counter relative addressing for store. Right? Okay, then I come to another topic that is quite important, which is the conditional execution. Now, for conditional execution, there are two parts. Okay, in C programming, you'll say, okay, if X is less than Y, add these two numbers or whatever, right? So in assembly language, you can have something similar. We have to sort of compare the X and Y values. So what you can do is you can do compare. So one of the values you put inside one register, another of the values you put inside another register, or you can indicate it, hard code it, and so on. But what the net effect of comparing does is it's subtracting it, right? So if you say, okay, if X is less than Y, and one of the values is X, another of the value is Y, if X is really smaller than Y, you will end up with a negative value, and then the N flag will be set, and then that will correspond to X less than Remember that for conditional execution, the first part is to set up the flag. If you don't do compare, you could also have set up the flag by the S subscript. So sometimes, especially in a loop, we have like SUBS, for example. If you have noticed, always in the loop, we always have, okay, this one, this one is an endless loop, but when we have a conditional loop later on, you will see that it's always SUBS. Right? Then after that, the part 2 is the execution part. Now the execution part, the relationship that you are interested in, less than, greater than, equal, okay, is combined together with the instruction that you want to execute. So the first part is this, then the second part is this, okay? And also the actions, which is the instructions, and then also the condition itself as well. So the original relationship, you do the compare, but the actual relationship together with the actions, you actually specify in an IT block, or if your instruction is a branch, then you just have a B with the suffix. The condition code suffix is listed here, right? So B can be combined with any of this. So it's not that so many branch instructions, but it's just a B combined with different condition codes. And then you don't really need to memorize any of this, but if you need to use all these things, you will be given as an appendix or as part of the reference section of the question, for example. But you just have to understand the concept that, for example, equal not equal is the most obvious one. The reason why when you are equal, the Z flag is set is because if X is equals to Y, X minus Y will become 0. So that's why the Z flag is set. And then basically, if you do BEQ, that instruction will happen, the branch will happen. Or if you actually put it in IT block, that instruction will be executed. Okay? So just be aware of the conditional execution. Okay, I just go on a little bit more, then we can look at some problems. Okay, I think all this you all can read yourself. Okay, notice that in Linky, because the instruction, the addresses are very far away from the program, we always have to do we sort of never do program counter relative addressing. We always do the offset addressing, you notice. Logical, you can read yourself. This diagram is important for the shift and rotate. Okay. Be aware of the difference between arithmetic shift right and logical shift right. Okay. Okay, then the last part here is important. Okay, the last part here, the pre-index post-index, right? The exclamation mark and the one that close bracket and offset is outside. So maybe look at the example directly. So you still have your base register, right? And then actually it's very similar to the original offset addressing. You still have to calculate your effective address, which is taking the value here added to this, right? Then after that, oh, okay, this 1004, I go and get the value and put it inside here. So that one is like pretty much the same as original offset addressing. But when I have this exclamation mark and it is pre-indexed, I actually change the value in the base register. No, in the earlier case, this one doesn't change. Okay, and this automatic update is very useful when I actually have a list of numbers that I need to process, for example. So I will sort of automatically, if I have a loop that goes round and round, I will be able to process different values in the list conveniently. And quite often we do that, right? So pre-index means I have to do the work first, so I actually calculate this first and then take the value from here. Post-index, which is the other case here, is I use it first. So this is the value there. This is the value that gets transferred. Okay. Then after that, then only I update this. Okay. So that's the post-index. And this is very useful for, let's say in this case, example 3, where we want to add a list of numbers that is stored in memory. And then I went through this example in detail. If you go and trace it yourself again. But essentially, because of this post-index, it was very convenient. My R2 value can change automatically so that I can access the different values and then do the addition. Right? Okay, so with that, right, we if you understood all this, right, then you say, okay, now I'm ready to take exam, right? So I'll just show you some example questions, right? It doesn't matter which year and all that. You can find all the exam papers in the library, right? And remember that 2-3 years ago, it is not 2028, it is 2024. So you will either find it as TEE 2024, and then in the earlier years, it was EE 2024E or something like that. Okay, so let's say you have this problem, right? So actually, we do expect very strong understanding of what's happening in memory and what's happening in processor register, similar to what I revised just now. Okay. Now, actually, since this one was like very long ago, that time we covered another addressing mode called register offset, which you don't need to know. So if you see like 2 registers inside the square bracket, don't worry, you don't need to know. Okay, so this one don't need to know, because like what I covered just now in the lecture 4 don't have 2 registers inside, right? Inside the square bracket. Okay, so now let's say you have this situation, and then you say, okay, you want to do part 1, right? And then you have to understand the instruction, right? So this instruction seems quite scary, quite complicated, so many things, you know. You are quite used to add with 3 registers, then how come this one got this? Then you should remember your operand 2, right? And operand 2 actually is this part itself. So this whole thing is operand 2. And meaning that you are going to get the value by taking the value in R1 and shifting it to the left by 4. And then the other number that you're adding is the value in R0, which is 8, right? So if you look at the working, it is the value in R1, which is 8, plus the value in, the value in R0, which is 8, plus the value in R1, which is 30. Shift left by 4 is actually like multiplying by 2 to the power of 4. But if you actually shift left by 4, you know that you introduce a 0 at the end in hexadecimal, because and definitely please know how to map between hexadecimal and binary at the back of your hand. Okay, we expect you to not spend more than 2 seconds converting between hexadecimal and binary and vice versa. Right? So so you know when you shift left, you introduce 4 binary zeros, but actually it's 1 hexadecimal 0. And then when you add it together, it's 308, and then definitely that 308 will go into the R3. So this kind of question, please don't get it wrong. Okay? You should be able to do this in 1 minute and then score the marks for it. Then the second question is a little bit more challenging, but we just discussed it just now, the pre-index addressing, right? So you know exactly what to do for this. So there will definitely be some of these kind of basic questions to let you score some easy marks. So this kind of thing, please don't throw it away, right? If even this one you get wrong, then God bless you, right? Because these are the basic stuff, right? Yeah. Okay, so so this one, right? Effective address. Like what we said just now is you just add it together and then you get the effective address, and that's where you're getting the value from. So 3004, which is this value, will be loaded into R3. Okay. And then the important thing to bear in mind when you have this thing is the fact that your base register value gets updated, okay, with the effective address. Okay, now the next one, the push, is a little bit more complicated. But you also have to pay attention to the fact that this piece of information is given to you. Currently, the stack pointer has this value. Conceptually, okay, maybe I draw it in a later slide. Okay, maybe you don't need to draw it here. So this one is the stack. Okay. And the stack is in memory, right? And this is the initial stack pointer. At first, when I say the SP points here, it's the same as saying that SP has this address inside. Right? SP has that means it's the same as saying SP is pointing here. So when you want to push two register values, you're going to store them here. Now the question is, the R1 value come here or come here? The R3 value come here or come here, right? So the simple rule of thumb is that the lower number register value comes to the lower address. So the R1 value will come here. And then the R3 value will come to this, will come here. And if you check back here, R130 is here, and then the 1, 2, 3, 4 is the R3. Okay. So, of course, before that is you will actually decrement by 4 first, then store this value inside, then decrement by 4 to store this value inside. And then at the end of the day, the stack pointer is actually updated to become this value. Okay, so don't forget that the stack pointer now points here. It always points the top of the stack, the last value that went in. Right? So no longer there. But now that the stack pointer is pointing there. The stack pointer pointing there is the same as saying that the value in the SP register is this value. Right? Okay, so that's some simple questions. We don't. Okay. Then now maybe let's look at some bigger questions, right? So bigger questions usually will give you some simple problem, and I think this problem is a little bit similar to your assignment 1, but doesn't matter, you know. Whatever the problem is, you just read the question and understand it. Usually it's something fairly simple. So I ask you to write an assembly language program, right? And this is the one that you should be able to do in 15 minutes or so, right? Okay. Of course, 15 minutes include reading the question, so you have to learn to read fast as well. Don't spend 15 minutes reading the question and have no time to do it. Now with practice, you can do it. And so okay, and then some simple strategies that I can share with you, right? But okay, let's read through this first. You can try and sketch some picture to help you understand, right?
Okay, so I want to compute, let's say, mean and variance. I am given some simple formula, right? And then I have a list of integers. So I quite often will involve memory and processor, so you can always happily draw it. Right? So let's say I have 6 numbers, maybe 4, 3, 5, 1, 2, 1, 2, 3, 6. Okay. So maybe this is my list of numbers. Okay. These are my list. And then of course every single memory location has some address. I am not told what it is, I don't really care. And it says that it's stored in main memory starting at location numbers. Actually, you can also make sure you revise your tutorial questions because it also had a few problems like Fibonacci and all those things that you can look at. Okay. So whatever it is, this address is referred to by the label numbers, right? And then it says that, hey, the value of n is how many numbers? In this case, there are 6, 1, 2, 3, 4, 5, 6. Okay, so there's another 6 here. And this one is also stored at some address, and this one is n. Okay, so this one is location n, right? So when you read the question, you can try and interpret it and draw some sketches to help you. Then it asks you to compute this mean and variance, right? And then after that, store the mean and variance in 2 other words. Okay, so the mean comes inside here, the variance comes inside here. And then this one has certain address, and then this one is answered. Right, so this label answer is telling you where to put the answer. So you have to understand what you need to do, right? Now, if I ask you, you want to calculate the mean, and then of course everybody knows this summation sign, right? Means I have to add all these numbers together. And then, do you think there will be a loop to do this? We just saw at the end of lecture 4 that there was a simple example, there was a loop, right? So once you see that there's a loop, and actually if I go back to, I forgot to mention the thing to look out for in a loop. Notice that in a loop, there are certain basic things. There's a label, and there is usually a counter how many times to go around the loop. And then normally you subtract by 1 every time you do the loop. And then there's an S there. So it's actually the S suffix, meaning that I want to update the condition code flags. You know that setting up the condition code flags is the first part of a conditional execution. In this case, I don't need to do compare. Actually, by here, I will know that if I hit 0, that means I have finished the number of times that I am supposed to loop. And the Z flag will be set, and the EQ condition will be satisfied. This GT is greater than, so it's actually another condition code that can be used in this case. As long as the value in R1 is greater than 0, basically the resulting value here is greater than 0, I will continue to loop, right? So I will actually satisfy that condition and loop again. So here can be GT, can be branch if not equal to 0, but then once it's equal to 0, you will not branch, you will fail the condition. And do the next line. So if you know the standard kind of format for the loop, then you can very quickly, in this case, write out the code. Yeah.
Will you provide the GT
I think the simple ones for looping we may not provide, but if you actually need to do very complicated logic, we will provide. So I think the looping one, the easiest one is probably BNE, for example. So BNE is probably more natural to use. I haven't hit 0 yet, not equal to 0, I continue to do. But GT will have the same effect greater than 0. Okay, so now if you look at the solution, right, that we expect from you, write all this down in 20 minutes or less, okay? Now the one key thing that you should know is the first part of the program is initialization, okay? So the first part is initialization. Okay. Now initialization usually requires some loading. And you can see that I'm doing a program counter relative load for my number of times to loop. I'm setting up base registers. Okay, so R1, R3, whatever value inside, they are actually base registers. Because I want to use them to actually load values on a list. Okay, similar to the earlier cases when I actually, if they are base registers, that means I expect this R1 and R3 to be within square brackets when load and store, right? But before they have the required values, I have to do the pseudo instruction kind of load because I want the label values itself to go into R1. So whatever this address is, okay, let's say this one is ADDR1, whatever hexadecimal value. I want that ADDR1 to come inside here, right? Whatever this thing here, this address ADDR2, I want that thing to come inside here. So, and then after that, I initialize this counter, this accumulator. Okay. Now then, the first part here is a loop. Now, essentially, this part is, of course, depending on your problem. In this case, it asks you to calculate mean and variance, right? So you calculate. So this is the part that's calculating mean. This is the part that's calculating variance. Okay. Other questions will have other things for you to do. Initialization will always need to be done. Okay, so if you jump straight in and do initialization, you straight away get some marks already, right? Now then, of course, in this case, to calculate mean, we need to do post-index addressing. So we use the base register, R1 here, and then after that, when we store, we also use the base register store. So of course, here is a loop, and then if you look at the standard format, you know there's a loop, right? There's always sub S and there's BNE, for example, is the easiest thing to use. You always have a label. So, you know, the rest is you can do whatever, add or multiply, whatever. Then you divide, since this thing needs a divide. And then it's done. And then this one requires this value here. So I need to run through the loop again. But since when you do post-index addressing, you actually modify the base register, right? So now your base register is no longer that first value. So I have to reset back the base register to the first value. So that's why I have to reset back the base register to the first value. So if you understand the concept of base register as tracking
the address where you get your individual numbers from, then you know that you have to reset it, because at the end of this loop, it was actually pointing to the last number already. So you have to bring it back to the beginning. And then also this value here, I was using R0. I was using R0 here as my loop counter, and actually I was decrementing it. So you have to remember to go and get back the 6. Don't go and happily use it. So like here, the first part here, I have to divide by n, I have to load it again. And here I have to, actually here I don't have to load again, but then just to be careful, I load it again. Then after that, here's the second loop, again standard format. Sorry, the next line. Okay. So all these things you all should be able to do. And then this one is a base register after I reset it. And then this one has some multiplication. Then after that, some division. Then after that, the last part here, this one is storing with post index, meaning that I store it here. Then automatically the R3 jump to this second place. So the next time I store to the R3 is actually going to the second box. Here, the first store was going to the first box, right? And then you actually automatically incremented this R3 value. Okay. So, you know, should be able to do it very quickly once you get the hang of it. So very quickly now, I go to another question, right? Again, something quite straightforward, like calculating temperature values and so on. We learned this in primary school, how to convert Fahrenheit to centigrade. But here it says that use a subroutine. Okay, so I want to be able to write VL and all that. And then here it says, hey, Fahrenheit has 2 decimal places. Now one thing that may be helpful to know is we will never ask you to do floating point operation in assembly language, right? You always deal with signed or unsigned integers. So if you have 2 decimal places, we would actually need to scale it by multiplying by 100 in this case. So here one part of the question says, hey, what do you do to convert a 2 decimal floating point value to an integer, for example? It says, later on we'll say it's multiplied by 100, and then later divide by 100, and so on, right, the data conversion. Once again, there's a list of numbers, location, in, val. So in this case, the problem now is I have some list of numbers, I have some starting place, it is in, val, and then whatever value here, let's say 212 Fahrenheit is supposed to be 100 Celsius. So let's say I have multiplied by 100 is 21200, and then this one has some address. This one is out well, where I'm supposed to put the centigrade value. In the end, I'm supposed to get 1000 here. 100 times 100, right? So, so if you understand the question and you know what's supposed to happen in memory, then you can work on it. And now I think you get the hang of it, you should be able to do this very fast. But the twist here is that I have a subroutine. And my subroutine has a name. At the end of it, you also should know the standard format for subroutine. At the end has BXLR, right? I do the subtraction by, because the formula is 32, if I multiply by 100 is 3200, okay? Then after that, I multiply by 5, divide by 9. Multiply always needs the operands to be in registers, so I cannot hash 5, hash 9 and all that. But basically, this part is the initialization that we always do. Okay, so always, for sure, we have to do initialization. And initialization usually has some loads, the correct kind of load. Either it's program counter relative load or pseudo instruction kind of load. Usually the offset addressing kind of load is in the main part of the program. The initialization one is usually program counter relative or the pseudo instruction type. Okay, so anyway, when you get the first value, so anyway, in this case, since I have a list of numbers, I need to do loop, and then you know the standard format for loop is loop, and then sub s, and then some BGT or BNE. And then the work that is done inside, usually you have to, so R1 and R2 are the base registers. Because I'm reading value from a list in val, and then the other out val list, so these two are base registers. So if these two are base registers, you would expect this R1 and R2 to be square brackets for the load and then for the store, right? And this is the calling of the subroutine, you know, is BL, right? And then the conversion is multiply by 100 first and then divide by 100 at the end. Okay. So hopefully this gives you some confidence that it's not impossible to do it in 20 minutes. But you have to practice. You cannot read your lecture notes like storybook, then walk into the exam, maybe you won't be able to do it in 20 minutes. But if you practice a little bit, you sure can. Okay. In the last 5 minutes, because I think some of you have tutorial at 7:30, I just want to talk a little bit about the non-assembly language parts as well. Because assembly language is one question, there will also be another question related to part 1. So part 1 we covered pincell, we covered C programming, pointers. Yeah, I think I want to revise I want to revise the C programming thing a little bit, just quickly. Okay, remember when you have two-dimensional arrays, right? Let's say you have this 3 rows, and each of the rows have 4 elements or 4 numbers. So those numbers, they are actually stored row by row. So the 1, 2, 3, 4 is like that. The 5, 6, 7, 8, and the 9, 10, 11, 12. Then when I say values 1, 0, it is going to refer to this. If I say values 2, 0, it's referred to this. And if I say values 2, 3, remember it starts from 0, 0. And then the third value is actually subscript 2. The fourth value is subscript 3. So 2, 3 is the last one. 2, 0 would be this 9, right? So just remember how a two-dimensional array is stored. Okay. And then pointers to structures, I think you all use a lot. Okay, then what's a pointer? It is just a normal variable, but what's inside is an address. It's an address of a variable, and the variable has a value. So when I do star PV, I end up with a 5. If I say PV alone, it is this value itself, right? Okay, so pointers is one thing. Then we also look at pincell, look at GPIO, but I think GPIO is pretty recent. All of you have, you know your read value, set value, clear value, set mask. You know your interrupts, the fact that you have to use LPC GPIO int pointer to a structure, then you put right arrow to the GPIO register. I can show that to you briefly, right, before I hand you over to.
So you know the syntax of the pincell, MPIC and all that, enable IRQ. You know the
GPIO registers, for example. Okay. So anyway, here you will notice that whenever we have interrupt, we have used this pointer to the GPIO structure. Then we have the right arrow, and then these are the members of the GPIO structure. Right? So if you look at LBC 17xx.h, you see all the structures defined. Okay, in the last couple of minutes, I'll just sort of show you this another question that is based on, let's say, pin cell, right? And refresh your memory on the important principle. So choosing the function, like in this case, you are asked to enable all these functions. So this is just turning on the switch for those functions. You know that this is the functions here, and therefore, for bits 220 to 27, wherever they may be, somewhere here, I need to make them 1010. Sorry, 0101 0101 0101 01. So bit 20 to bit 27, right? So now don't affect the bits that are not relevant. Okay, so don't go and just equal sign and assign these bits inside and then cause everything else to become 0 or change or whatever. Don't change the bits that are not relevant. Okay. So we learned that if you want to get this bit pattern inside, notice that there are currently some of the values may be 1 already. So if I say go and take the original value and all with a bit pattern, I may end up with 1 1 1. Some of them will become like that, and this is not what we want. So in order to be safe, we need to clear those bits first before we OR with this value, or we make those bits all 1 and we end with this value. Then we will end up with actually this bit pattern being inside those bits of interest, right? So just remember that don't anyhow assign, because assign will just equate everything. So like for example, the bit 20 to 27, right? So once again, I emphasize that you should be able to switch between hexadecimal and binary in 1 second, right? So straight away you will know that this is a 5, and this is a 5, hexadecimal 5 5, and this is 1010 is an A, okay? And of course this is 0, so all these are A's. So this is the value inside here. Originally there's some value, and you are told in the question that the address of the register is already in R0. Okay, so the R0 is like the base register now, right? Get the whole bit pattern into R1. You need to get it into the register before you can play it or manipulate the bit. So bit clear. Bit clear is the instruction where all the ones are made 0. So when you actually do this, essentially, if this value is sitting inside, after you load it into R0, I think, no, R1. After you load it into R1, you are forcing this 8 bits to become 0, only those 8 bits. So bit clear is actually very useful for only affecting those bits that you have as 1, because this FF is actually 8 ones inside them. And then, of course, there are 4 zeros in front, and all the zeros at the back. You're saying don't touch those. Touch only this one, cause them to be zeros, and after that you OR this value inside, and anything OR is 0 doesn't change, and then you store it back into R0, and that's how you end up with having exactly the bit pattern that you want in those bits, and then not changing the rest. Okay, the rest unchanged. change. So this principle was also emphasized in tutorial 3, so don't forget that. Okay, okay, so hopefully this short revision is useful to all of you to sort of understand what are the important parts in part 1 that you all really need to know about. So I'll see all of you at the exam on the 2nd of December, I think. It's still like 2 weeks away, I think. It's quite late in the exam schedule. So I think, okay. Any quick question? Any quick question? Close book, no formula sheet, nothing.